Thanks for watching my course about algorithms in JavaScript. You might have heard of algorithms in school, at work, or just in passing, but what really is an algorithm? Algorithms are methods that take input or data, perform a series of tasks, and stop when the answer is found. They're used in day-to-day problems like finding the shortest distance to work and used to calculate the best response to Google search. Though not all algorithms are created equal, it's important to not only know which one to choose when faced with a problem, but the true power is understanding how the algorithm works itself. Maximizing your application's time and space can sometimes make or break your system. Some algorithms perform better than others, and some can be implemented incorrectly, leading you astray. We review many different types of algorithms, including sorting, searching, and breaking down complex problems. We implement recursion, loops, and classify items. The algorithms shown in this course barely scratch the surface though. There are so many and each have their pros and cons. In this course, we speak a lot about big O notation. Big O notation is a special notation that tells you how fast an algorithm is. But what does that really mean? It does not tell you how fast in seconds your algorithm will run to completion. No, it lets us compare the number of operations it will make. It tells you how fast the algorithm will grow. It defines how quickly the runtime of an algorithm increases as the size of the input increases. Essentially, Big O tells us the worst case scenario our algorithm will run at. In this course, we work with slow Big O notation algorithms in selection sort and extremely fast Big O notations like binary search. In the end, what I want you to take away from this course is a new way to face problems. Algorithms teach you that large problems can be broken down into smaller problems. Sometimes we try to tackle problems head on and become lost in a tangle of if-else checks. Instead, we should take a step back and figure out what is the root problem and how can we write a maintainable solution that will scale efficiently. Let's write a counter function. Inside of this function, we'll do a for loop. We'll do let n equals 0. While n is less than or equal to 10, we're going to n plus plus. Then inside of this, we'll constant.log our n, and now let's invoke our function. Our constant.log shows us that we were successful in creating a simple looping counter function. Let's refactor this to use recursion now instead of a loop. The first thing we'll do is comment out our function call here and remove our for loop. And we're going to return counter n plus 1. And we'll pass in an n as a parameter to our counter, and then pass in 0 to our function call. Recursion, simply put, is when a function calls itself. As we can see here, we're returning the result of our own function, adding to the argument by 1 each time. Adding a constant.log here with n will give us the same result that our for loop gave us. However, when dealing with recursion, it's important to understand two concepts of a recursion function. It needs to have at least one base case and one recursion case. The reason why we commented out our function call is if we were to run this function, it's going to enter an infinite loop. This is because we don't have our base case yet. So to if n equals 10, we return our function. Now with that in place, we can invoke our function, and we'll see from our console.log that we get numbers 0 through 10 successfully. And this is because we have our base case if check to stop at 10, and a recursion case to continue until we hit that 10. Now, as a side note, there's no performance benefit to using recursion. In fact, loops are sometimes better for performance. On the other hand, recursion can sometimes be easier to understand. If you struggle to understand what the base case is supposed to be, just think of it as what are you trying to get from this recursion function? In our case, we wanted to create a loop that counted from 0 to 10. So 10 was the goal, and that was our base case. Let's run another example to understand this. Let's say that we had an array of arrays with numbers in them. And our job is to look through the arrays for the number 6. If it's anywhere inside of this parent array, then we need to return true or just the string yes. I've already gone ahead and created this function for us. I've called it find6. It's going to take a list of items, as you can see down here. Inside of it, we're going to say, just start off with initially, it does not have a 6 inside of any of the arrays. For that first set of array, we're going to step through each one. So we're going to get this first array and the second array inside this first for each. And then once we're inside these two arrays, we're going to for each again, looking for 6. If we do have 6 somewhere in there, as we do on that second inner array, we're going to update our has6 variable, and that's what we're going to return. As you can see here that we get yes. If I change that to 5, our function switches to no. This accomplishes our task, however it's not very dynamic, meaning if we were to add this 6 around another array inside of here, we'll see that our function returns no when we still have a 6 in here and we want it to return yes. In order to accomplish this, we'd have to add another for each loop inside of here, where we say if it's an array, we need to do another for each inside of its contents. So instead of adding more and more for eaches or another type of loop, we can refactor this to use recursion. This entails getting rid of one of the for eaches and adding an additional if check where we say if A is an array, then we need to call this function again, our has6 function, passing in this level of array and assigning its return value to our has6 variable. Now with our console.log, we'll see that we're getting a yes back here, even though we have this third inner array. And it stays yes as we remove it, and goes to no if we get rid of the 6. Our base case, or the goal of our function, was to find the number 6. So this was our base case. We're basically repeating this simple logic over and over for the amounts of arrays that we have within our parent array, which makes our function more dynamic. And it's why it's said recursion can be easier to read and understand than just using loops. When working with divide and conquer, it's important to understand that these types of algorithms are recursive algorithms. And divide and conquer isn't a simple algorithm that you can apply to a problem. Instead, it's a way to think about a problem. When faced with a problem, you can think, how can I divide or split this problem down to its simplest form? Recursion powers this mentality because it requires a problem to be able to be broken down into subproblems and then returns or solves them up from the bottom. So let's create a function, we'll call it sum, that takes an array. We'll say let total equals 0, for let I of array, total plus equals I, then we'll return our total. Now console.log our sum, passing through an array of 1, 2, 3, 4, 5. Perfect, so we'll see that that gives us 15. We are simply just looping through each item inside of our array and plussing it onto each other, which gives us 15. So how could we use divide and conquer and recursion to break this down into smaller problems? Let's first think about what is the simplest case with our numbers. Well, if we had an array of just one number or even an empty array, that would be pretty easy to sum up. It would just be 0 or that one value. So this is our base case. Our goal is to move closer to this with each recursive call. So in order to remove an element each time we recursively call this function, we first need to make sure we're adding up that removed item to the remaining state of the array. And we'll do that by slicing off the rest of the array and then adding it to the first value of the array. Recursion is a first in, last out. So our function on the first return call returns a 1 plus sum array 2, 3, 4, 5. And then within that function, we're returning a 2 plus sum 3, 4, 5. It'll continue to do this until we reach our base case. We return 0, which is then added to the last number 5. Then it's 5 plus 4, which makes it 9 plus 3, 12 plus 2, and finally 14 plus 1, which gives us our value of 15. Recursion is nice because it keeps returning our new state after each function. Let's define an array of items we need to sort. Instead of it, we'll give it a 3, 2, 4, 1, and 6. Now before we create our selection sort function, we need to first write a function that loops through this array and gives us the index and the largest number. Then once we have that, we can use our selection sort function to create a new list, call this function, and then remove it from the original list. So for that first function, we'll do function find largest value, which will take a list. Then we'll do let LRG equals list of 0, let index of large equals 0. Then we'll do a for loop where we start with 1, and while our I is less than our list at length, we're going to increment our I. If LRG is less than list at I, then we're going to update our large value with that list of I and update our index of large as well. And then finally, we'll return this function, returning the index of large. To recap, this find largest value function takes an array of items, loops through that list, and then returns the index location of the largest value within this list. We start off defining the index and the item with the first item, and then if anything appears larger instead of our loop, we update it. Now with that ready to go, we can create our selection sort function. So we'll do that function selection sort, takes a list. Inside of that, we'll create a new array called new list. We'll define our new large item. Then we'll create a while loop where as long as our list has values inside of it, we're going to update that large item equal to calling our find largest value function passing in this list. That's going to return, and we're going to push onto our new list the return value from our find largest value function. Once we've found the largest value from our list, we want to remove it so we don't count it again as we push values into this new list that we've created. So after we remove this, we're going to return our function, which is returning the new list that we've created. With that in place, we can call this function instead of a console.log. We'll pass in our items to sort, which we created earlier, and we'll see that our array is now sorted 64321, which is correct. Now let's go back and review this function one more time. The first thing we do is create a new array. This is the array that we're going to return with this function that we see printed here in the console.log. The second thing we do is use this while loop where we call our find largest value function, passing in the current list that we have been provided. Once this find largest value function returns, it gives us the index location of the current largest item, which we push onto this new array, and then we also remove it right after that. And because we need to call our find largest value function for n number of times, or in other words, we have to call our function a total of however long our list is, this gives our selection sort function a beginning big O notation of O(n). Then if we remember, our find largest value function also has a loop inside of it. Stepping through another n times with its provided list, this makes our big O notation O(n times n, or n squared. Selection sort gets the job done, but it's not very fast. Quicksort and merge sort are more efficient and have a notation of O(n log n). Quicksort is a much faster sorting algorithm than selection sort. It's frequently used in real life and is built into some languages like C automatically. It's a divide and conquer function that uses recursion to break down the array into smaller pieces, then connects them at the end. The three fundamental components of quicksort is working with an array that holds the elements less than the chosen pivot element, the pivot element, and then an array of elements that holds the elements greater than the pivot element. Let's begin by defining the base case of our recursion quicksort, which is going to be if our array is less than 2, let's return that array. This is because if our array has 1 or 0 elements in it, then there's nothing to sort. Now we can work on getting to this base case with the least amount of recursion calls. Next up, we'll define our pivot index by saying math.floor array.length divided by 2, and then let pivot equals array at that pivot index. You'll find that the most complex issue in quicksort is choosing a good pivot element. Choosing the wrong one can drastically decrease its performance. If at each step we choose the middle as the pivot, then we'll get to the result the quickest. We'll talk about this more after we finish out the function. Next up is creating our less than and greater than arrays that we'll push into. Next, we'll do the actual looping over each element in the array. So do let I in array. If our I does not equal our pivot index, then we're going to check for this value against the pivot. If it's greater, then we're going to push into the greater array. If it's less than, we're going to push this value into the less than array. We'll close out our function by returning a new array, spreading out the results of calling quicksort on the less array, the pivot, and then spreading the results of quicksort on the greater array. With a quick console.log calling our quicksort and some dummy items inside of array, we'll see that this quicksort function is working properly. Let's go back and review what we've done so far. First, we're choosing the middle element in our array, using math.floor so that we don't get a decimal index number, and using that as our pivot. This means that with each recursive call, which breaks down our array into smaller pieces, we'll always use the middle index. Then we have an array that holds the values smaller than the pivot and the items greater than the pivot. We figured this out by using this ternary here. Since we're already adding the pivot item in our return, the if check makes sure we're not adding the pivot item twice. I is a string and pivot index is a number, which is why we use the exclamation mark equals and not exclamation mark equals equals. Finally, in the return is where we are recursively calling our quicksort function to then sort the numbers smaller than our current pivot and items greater than our pivot. Inside of these function calls, our function picks a new pivot by finding the middle and creating two arrays, and so on and so forth, until we get down to our base case and return all the results back up. Now let's talk big O notation and the importance of the pivot element. When it comes to sorting, every single item in the array needs to be touched. We need to see how large or small an item is in order to know where it fits in line. So we know we're at least going to be O to N. What makes the algorithm faster is choosing the least amount of pivot items. The more pivot items we have, the larger our call stack gets. That height of our call stack, at best case, which is also the average case, is getting O log n, which makes our final notation O n log n. Worst case is having a pivot item for every single item in our array, which would give us O n again, or O n squared. Let's put a console log inside of the function to see how many times it gets called, and then we'll play around with two different types of pivot indexes. We'll do the last element and the first element in the array, and then we'll console log our pivot so we can count how many times we're pivoting. We see that by using the middle item as our pivot, we have a total of 4 items. If we instead always use the last element as the pivot, we see that we end up having 5 pivots and our function's called a lot more. If we use the first item, we're back to 4 and back to the same amount of calls as using the middle. So in this one set of numbers, using the middle and the first was the best. You'll find though that if you were to rearrange the numbers, you could find when the last element is better than the first or middle. There are multiple variables that affect the call stack height. Though using the first or the last will give you the worst case big O notation of O n squared when you're trying to sort an array already sorted, we see that we're at 5 pivot items for using the first item. We still have 5 if we use the last. However, if we use the middle, we only have 3. This is the same if we use the numbers flipped, where we go down from 6 to 1. We still have 5 for the first, and we'll have 5 for the last, but only 3 for the middle. So if you use a random pivot index or the middle index, you will on average get the best case scenario. Let's say that we have an array of numbers anywhere between 1 and 12, and inside of our array they're in no particular order. And let's say that we've been tasked to write a program that goes through this array looking for one particular number. If it exists, then the program will return true, and if not, it'll return null. Luckily, this isn't too hard to create, so let's make a search function that takes a list and the particular item we're looking for. We'll start off with a default value for our hasItem, which will return at the bottom. Let's create a counter that we can increment each time we loop over our items. And we'll use the for_of to do the actual looping of our list. The first thing we'll do is increment our counter each time we loop over it. And we'll have an if check in here where if our element matches the item we're looking for, then we set our hasItem to true and we break the loop. Finally, let's console log our counter to see how many times we looped and return hasItem. Down here, let's invoke our function inside of a console.log so we can see the result of our function. Awesome, so the number 12 is in fact inside of our items array. Our method we used here to search through the array is called simple search or a linear search. The big O notation is O n, which represents linear time. Big O represents the worst case scenario, and with our current search function, because the number 12 was towards the end of the array, it took us 6 iterations until we found the number. This is relatively fast with just a small sample size, but what if our list had 1,000 items, or 10,000, or even 1,000,000? Worst case scenario is our program would take 1,000,000 loops until it found our item. This has some real performance issues as it grows larger. And again, our algorithm grows linearly, or big O notation O to the number of items, with each item added to the list. So let's begin to refactor our function. First thing we'll do is sort our items from lowest to greatest. We'll see that when we console.log that our items are now in order from 1 to 12. Let's remove hasItem and add letLow of 0 and letHigh of list.length. We'll keep our letCounter, but remove the for_of loop and replace it with a while loop where we say while low is less than or equal to high, we're going to loop over our list, updating our counter. We'll say let mid equals math.floor, low plus high divided by 2. Let guess equals list at mid. If our guess is equal to item, then we found it and we return true. If our guess is greater than the item, then we need to update our high equal to mid minus 1. Else low equals mid plus 1. The bottom will constant log our counter and return null. Perfect. Our refactored search function gives us back true for the number 12. And if we add a constant log before our return, we'll see that it took us 3 iterations to find this value. This refactored function is now using binary search. Let's walk through this again and talk about what exactly is happening. First of all, binary search is an algorithm that has an input of a sorted list of elements. Instead of stepping through our list one element at a time, let's jump right to the middle of our sorted list and see if our guess is correct, too high, or too low. If we guessed it, then we're done. If our guess is too high, then we know we can ignore everything after it in the list. We can continue on in the while loop, now repeating the exact same step, but if we now have an updated high position, we get a new middle element and do the same check. In the case that it's too low, we can ignore everything before the midpoint. We continue on until we guess the correct item. This process of jumping to the middle of our list, ignoring the smaller or larger values and repeating, gives us a big O notation of O log n, otherwise known as log time. Logs are the flip of exponentials, and when working with running time and big O notation, log always means log 2. Since we have 8 items in our array, our search function will take at most just 3 iterations to find the answer, though some might take 4 because of our rounding down to a whole number is not exact. The true power of binary search and log time specifically is when our list grows. At 1,000 items, we only need about 10 iterations, and 1,000,000 items, we only need around 20 at most. Dynamic programming is a technique that helps solve a hard problem by breaking it into subproblems and solving those subproblems first. It's useful when we're trying to optimize something given a constraint. So for our example, let's say that we're going camping and we have a backpack that can only carry 4 pounds worth of stuff. Each item is given an arbitrary number value of what it's worth. What is the best case value of stuff we can get into our backpack given our 4-pound constraint? Every dynamic programming solution involves a grid. Each cell is a subproblem. So let's think about how we can divide this problem into subproblems. And before we get any further, I want to take a step back and say that dynamic programming is a hard concept. So don't worry if you don't get it right away. It will most likely take you some time to grasp the concept. The way that we can break this problem down into subproblems is seeing what the max items we can get into smaller sub-backpacks. For example, we'll start by figuring out what is the best case for a backpack that holds just 1 pound and working up from there. The first thing we'll do is make our constraint backpack weight of 4 be an array of weights 1 through 4, and another array with our items, so rope, tent, and food. Let's then make a function to create an empty grid we can see and work with. We'll start with an empty array, and then we'll have 2 for loops. One that creates the number of rows or items we have, and the second for loop that adds in the value of columns or constraints we'll have. Once we've created that, we'll return our grid. Let's assign this to a variable called matrix, which we can then console.log out and see what we have to start with. Perfect. So by putting our constraint and items into arrays, we can dynamically add arrays and values to our grid. As we see, we have 3 arrays, and each of those have 4 values. The 3 arrays represents a row or an item, and each 0 represents a constraint weight 1 through 4. So this first 0 is at location row 1, column 1, or looking at our grid image above, rope at weight 1. So let's go ahead and create our fill in the grid function that accepts a grid, and this is where we're going to use 2 for loops to step through each row and column combination to solve our subproblems. We'll also pluck out the value and weight of each item so we can use in our calculations. The first set of subproblems we're trying to solve is the rope row, which means we're trying to fit the rope inside of a backpack that only holds each corresponding weights, 1 through 4. Since the rope is only 1 pound, it fits in each backpack, which means our first row and column will be 1500 across each subproblem. We can do some pseudocode and say, if there's not a row before this current one, meaning this is the first time through, just use the value for this row-column combination. Of course, this only works if row is the first in the array, but for simplicity's sake, we'll just do this. Then we'll console.log our fill in the grid with our matrix to see what we've got so far. Perfect. Again, since our rope is only 1 pound, it fits in each backpack weight column, so we have 1500 across the first row. And remember, we're trying to maximize the value of the backpack. This row represents the current best guess for this max. So right now, according to this row, if we had a backpack of capacity 4 pounds, the max value we can put in there is 1500. Next, we'll do the tent row, which has a weight of 4 and a value of 3000. The tent does not fit in a backpack with a weight capacity of 1, 2, or 3 pounds, which means 1500, or just the rope, remains the max value these backpacks can hold, so we'll carry 1500 down. We'll say that grid row at column is going to equal the previous row same column value. Our console log shows us that these first weight combinations of 1, 2, and 3 we're carrying along the max that we have so far of the rope, 1500 across. So again, if the weight of the current item is larger than the constraint, in our case the tent cannot fit in weights 1 through 3, we need to take the previous max value calculated for those weight constraints. Then if our current item weight equals a constraint, as our tent, which weighs 4 pounds, and so does our last constraint backpack, we take the greatest value between the previously calculated item at constraint weight and the current item's value. We see that our console log shows us that we're getting 3000 here for this last column, which is correct because 3000 is a larger value than the one rope at value 1500. Now let's finish by doing the food row. We can see that our function is already doing some work for us. Since food is a weight of 3, it is taking the previously calculated largest value at those two weight constraints, which is just the rope at value 1500. Then since our food value is larger than the previously calculated value of 1500, we're inserting 2000. And to calculate the last column, we'll continue this if and say let diff equals constraint column minus 1 minus weight, and the current grid row column is equal to the larger of the previously calculated same row column value and the value of our current item plus the max value of the difference between the leftover weight and the current weight. Our console log shows us that our new max value for our backpack that weighs 4 is now 3500. If you missed that calculation, let's review it again. Since our food has a weight of 3, there's 1 pound left over for the 4 pound backpack. We found this out and assigned it to this diff variable. Next, we're taking whichever of these two are greater. The previously calculated max value at backpack constraint weight 4, which is 3000, and our food at weight 3 plus our currently max calculated value of 1, which was 1500. This gives us a value of 3500, beating out 3000. Our answer to our question will always be found in the last row, which is 3500. As a side product, we also now have the answers to what's the max value that could be taken with the smaller backpacks. What's nice about this dynamic programming function we've created is what happens when we add an item, such as an iPhone, which has a value of 2000 and a weight of 1. If we throw that into our items array, we'll see that we now have our grid made up of 4 rows, or 4 sets of arrays. And our max calculated for our backpacks are 2000, 3500, 3500, and 4000 for a backpack at 4 pounds. Let's conclude with some final thoughts on dynamic programming. Can the value of a column ever go down? No. At every iteration, we're storing the current max value. The value can never get worse than it was before. What happens if we change the order of the items? Each column row would be different except for that last row, which shows us the max. And remember, we need to go back and iron out that first item logic. Dynamic programming only works when each subproblem doesn't depend on other subproblems. And if we compare it against other big O notation algorithms, such as calculating every single combination of items, which is O2 to the power of n, if there were 32 items, that would be 4 billion possible sets, as opposed to 128 column row cells we need to loop over. Let's say that we needed to write a program that searched through my Facebook friends looking for the closest friend that owned a dog. So we want to first search through my immediate set of friends before moving on to searching through the friends of my friends. Remember, the goal is to find the closest friend relationship that owns a dog. So before we search through Henry's friend of a friend, we need to check John's immediate set of friends first. So looking over the information we have so far, I've got 3 friends, Henry, John, and Amy. Henry has 2 friends, Peggy and Kelly. John has a friend of Kelly, so Henry and John share the same friend. And Amy doesn't have any friends. Peggy, who is Henry's friend, doesn't have any friends. And Kelly, who is shared between Henry and John, have one friend named Claire. In order to solve this problem, we need to structure our data in the form of a graph and use the breadth first search algorithm. This isn't a graph that uses a x and y axis. Graphs is made up of nodes and edges. In our example, the people are the nodes and the relationship between each friend are the edges. Imagine all of these relationships are connected by arrows or the edges. Now let's write const graph equals an empty object. Then we'll say graph Tyler equals an array of friends. Graph Henry equals an array of friends. John with his friends. Amy doesn't have any friends, so she'll be an empty array. Same with Peggy. Kelly has one friend of Claire. And Claire doesn't have any friends, so she'll be an empty array as well. Perfect. This is how we can graph our data together. We flattened out all the nodes or people into this object and assign their value as an array of objects that show their friends and if they have a dog or not. In order to find the shortest path person that owns a dog, we need to work with a queue data structure. Queues work exactly as they do in real life. Unlike in recursion where it's first in, last out, queues are first in, first out. They work the same as stacks. You can't access random elements in the queue. Instead, there are only 2 operations, enqueue and dequeue. Now let's go ahead and create our breadth first search function. This function is going to take a name, and the first thing we'll do is create our queue data structure. So we'll say let search queue equals an array.concat graph at name. Next, we'll create an array of all the searched individuals. And we'll say while our search queue has something in it, so .length, we're going to loop over each one. We'll say let person equals search queue.shift to grab the first one in the queue. If our person that we pulled from our queue is not already in our searched array, then we can check to see if this person has a dog. If they do have a dog, then we found a person and we're going to return a string that says this person has a dog. If not, then we're going to concat their friends onto the back of our search queue. So do .concat graph at this person's ID. Then we're going to push this person into our searched array so we don't go through them again later. If not, at the end, we're going to return a string that says there are no friends that have a dog. With this in place, let's do a console log with our search function passing through my name so that we begin with Tyler. Perfect, it looks like Claire has a dog. Before we go back and look at our graph data, let's go through this function one more time. The first thing we did was create a queue using an array. We added all of my immediate friends into the queue, so we began working with Henry, John, and Amy. When we get to the while loop, we have 3 items in our queue we need to loop over. The shift mutates our array or queue by taking the first item out and returns it. So person is being reassigned within each loop with the first object in our queue, while also removing them from the queue. In order to avoid cycles, we check to see if we have already checked this person by looking through our searched array to see if they're in there. If our person has a dog, then we return this string. If not, then we need to concat or push this person's friends onto the back of our current queue, and then push them into our searched queue, which again helps us avoid cycles. If no friends have dogs, then we return this string. We know that Claire is 3 levels deep. So if our function is working properly, if we were to change Peggy to have a dog, our function should return Peggy because it's my friend Henry's friend, and we see that Peggy is returned from our function before Claire. And if nobody has a dog, so Claire doesn't, neither does Peggy, then we should return there are no friends that have a dog. Let's say we needed to write a function that, when given features of a fruit, we need to make an educated guess on what this mystery fruit is. Let's make our function called determine fruit and destructure two fruit features that will get size and redness. Then we'll create our key, which is an array of currently known fruit and their attributes. So right now, let's say that we only know about grape, which is a size of 1, a redness of 0, an orange, which is a size of 2, and a redness of 1, and a grapefruit, which is largest, size of 3, redness of 2. Then we'll constant log this function, passing in the features of a grape, just to make sure we're getting a grape back from our function first. Perfect. The algorithm we'll use to figure out what fruit the provided fruit features most closely represents is called the k-nearest neighbors algorithm, or KNN. The KNN algorithm changes the way we think about classifying items. It works by finding the shortest distance between the provided set of features and our currently known items. By finding the closest relatives to our provided features, we can make an educated guess on what this fruit is by these close neighbors. It might be easier to comprehend by placing this on a graph. Since we're only working with two features, this is a two-dimensional graph. Along the x-axis is our size of the fruit, and the y-axis is the redness. Grapes are small and not red at all, so it's towards the bottom left, while grapefruits are the opposite. When we want to classify mystery fruits, we can imagine placing it on this graph and then finding its closest neighbors. The closer the neighbor, the better chance we have that we are correct with our algorithm. Let's write our function that will calculate this distance between our mystery fruit and our known fruits. We'll call it calcDistance, and it's going to take one parameter. We're going to return the math.square-root of data.reduced. Our accumulator will destructure two items. Then we'll return our accumulator plus math.pow, init minus test, squared, and 0. Perfect. Now let's talk about this because that was probably pretty confusing. The metric we're using to calculate the distance between our items is called the Euclidean distance. This formula is to subtract the same features of our mystery item against the controlled fruit features, to then take this to the power of 2 and add it to the other features doing the same thing. When we're done doing this to each feature, we take the square root. The smaller the number we get against a neighbor, the closer it is to it, meaning the more likely our mystery fruit is probably that closer, smaller away distance fruit. Now let's actually apply this calcDistance function against our controlled fruit. So we'll destructure name from fruit.reduce previous current. We'll say let current cal equals calcDistance, passing in our two feature sets, size as well as redness. Then we're going to return whichever one's smallest, either the previous or our current calculated distance. We return a new object with a name property and a dist. We need to work with the initial objects. We'll say name fruit at the first one, .name, and then we're going to do our calcDistance as well again on our two feature sets, size for the first one, as well as redness for that first one as well. Now that we have this, we can return a string that says this is most likely a, and we'll say name. A quick look at our console log, and it looks like it's working. We are passing in the features of a grape, and that's what we're getting back. Let's walk through this again. Our reduce loops through each controlled fruit. It applies our calcDistance formula against each of the controlled fruit to find its distance from our mystery fruit. We check this value against the previous smallest value, initially starting with the first item in our fruit array, and the smallest one wins out. A console log shows us the distance we're getting back from our Euclidean distance function. As we can imagine, the 0 distance is winning out because it has the same features as our controlled grape. We can play around with different scenarios and see what our algorithm tells us the best guess is. Let's wrap up with some final thoughts. Picking the right features is important when using the KNN algorithm to classify an item, and our algorithm becomes smarter as we add more features to calculate distance. Also, ideally we would not just use the one closest neighbor to guess what the mystery fruit is. The more controlled data points and features you have to work with, the better. You might find the closest 5 neighbors and see which controlled fruit of those 5 appear the most. There is no magic number of neighbors, though a good rule of thumb is the square root of the number of controlled items you have. Let's say that I own a restaurant that sells pies, and lately I've been having trouble making enough pies for the day. Sometimes I make too much, and sometimes too little. For the past few days, I've been keeping track of the weather, if it's a weekend or not, and how many pies I sold that day. So if it was a weekend, I put the number 1, if not, it's a 0. The smaller the temperature, the colder it was that day, and the total number of pies I sold. Using this data, I want to calculate how many pies I should prepare for today. In order to do this, we first need to have a function that will calculate the distance between today's data and our previous results array of data. This calcDistance function implements using Euclidean distance to calculate the distance, or in other words, puts a number to how similar today's data is with our previous results. Let's begin writing this function by destructuring the first and second results we'll get back from our calcNeighbors function we need to create. Passing through our previous results and today's information, we'll say it is a weekend and the temperature outside is mild. Let's create our calcNeighbors function, which we know takes results, and let's destructure today's information. We're going to return the results of reducing over our results array, which inside of here, we're going to call our calcDistance function over the features that we've defined, which include is it a weekend and what's today's temperature. Once we have those features outlined, we're going to return a new array each time, spreading what we've currently accumulated, but adding a new object with a dist property that shows our calculated distance. At the end here, we're going to sort so that we get the smallest distance object first. This way, when we destructure first and second on line 19, we're getting the two closest neighbors. So again, we're looping over each of our data sets and calculating how similar today's information is against the previous data. We return a sorted array that puts the closest neighbors, meaning the most similar to today's data first. This algorithm of calculating the distance of neighbors is called the k-nearest neighbors algorithm. And then if we console.log first pies plus second pies and divide this by 2, we'll get the number of pies we should make for today. This process of finding an n number of closest neighbors and then finding the average between them is called regression. It's a simple but powerful way of predicting future events based on past events. In our example, we're only getting the average of the two closest neighbors, though this is just one use case and there's no magic number of neighbors to get the best answer. A general rule of thumb is to use the square root of the number of items we have to know how many neighbors to calculate against. And as you can probably imagine, the more features we have to work with, the more accurate our function will become. There's nothing special about having just 2 features of today.